We now continue our treatment of the electric potential by developing the relation for the electric potential for a point charge at some location. So let's say this is our source point charge here, Q. And let's say that we are interested in figuring out what the potential is at this point of interest here, which we will say is a distance r away. So the recipe is going to be similar to like what we were doing when we defined the electric field. We will say that the electric potential is defined to be the potential energy due to this source charge plus some hypothetical test charge, and then we divide the test charge back out. So in our imaginations, we imagine sticking a test charge right there. And we remember that the electric potential energy for a pair of charges is K, Q, this for this charge here, and then this hypothetical charge that we put here would be QT over R, and then we would divide the whole thing by our test charge, and the test charges had better cancel out because we only made them up in order to figure out what the potential would be at this point in space here. So we end up with KQ over R. Or if you prefer, 1 over 4 pi epsilon naught over R. And again, because we have already made the choice that the electric potential energy is 0 at infinite separation, we will have the default choice that the electric potential, when you are infinitely far away from our point charge, has been set equal to 0. The little circle over the equal sign means set equal to. So what I would like you to think about for a moment is imagine what the equipotential surfaces would look like for our point charge. What kind of shape would they be? And if you want to get extra in on it, think about how the spacing would vary, say, with a constant step change in voltage, like say going from 10 volts to 9 to 8, that kind of a thing. Okay, so hopefully you came to the conclusion that, say if this is my test charge here, that my equipotential surfaces, so these are surfaces of constant voltage, are spheres. And for the same decrease in voltage, the spacing gets bigger and bigger the further away we get, because it falls off as 1 over R. So again, remember our convention here that I'm drawing in 2D cross section, but these surfaces are spheres. So say that this would be, everywhere on this surface would be voltage V1, V2, V3, V4, etc. If this is a positive charge, all these voltages will be positive. This will be a bigger positive number, then a little smaller, a little smaller, a little smaller. If it's negative, then it might be, say, like -5, -4, -3, -2 volts, something like that. All right, so let's say that you have more than one charge, and this is where we're heading with looking at voltage here, is because voltage is a scalar, but it does obey superposition because it's mathematically derived from things that obey superposition. it's a lot easier to just add up two voltages because there are no components to take. Makes it a lot easier to do. So for instance, we could imagine our friend the dipole here. So let's say we have a charge plus Q here, and then we have a corresponding charge minus Q here. So the first thing to ask yourself is, what would the equipotential surface for V equals 0 volts look like, and where would it be located? Pause and get back with me on that. Okay, well, it turns out that V equals 0 volts will be the plane that bisects. Maybe we can do a little better job than that. Here we go. It would be the plane that bisects the two charges. This is because at any point in space, let's say we're interested in the voltage at this location in space right here. Let's make it a different color. There we go. Let's say that this distance, that this is Q1, this is Q2, so this distance here would be R1. That distance there would be R2. To get the voltage at this location, we would be adding up the contribution from charge number 1 plus the contribution from charge number 2. So this is going to be KQ1 over R1 plus KQ2 over R2. In general, if you have more than two charges, you'll probably write it as something like V equals K times the sum over all of our charges, Qi over Ri. Again, like I say, this is just a scalar, and so that makes things a lot easier for us to compute. Alrighty, so then so the only way we can have 0 volts then is, since Q1 and Q2 here are equal and opposite charges, would be if our distances were the same. Anywhere on this point, on this plane right here, it'll be the same distance from this charge as to that charge. So that's why it's V equals 0 there. Anywhere to the left over here, the voltage is going to be positive. Anywhere to the right over here, the voltage is going to be negative. Whoops, negative. All right. So the next thing to ask yourself is, imagine that you are sitting quite close to one of the point charges. What would the equipotential surface look like then? Okay, well, if you're really close to a point charge, then the distance to that charge is very small. And a very small number in the denominator is going to make a very big contribution, which means that really close to one charge, the other one doesn't matter so much. So the equipotential surface there, this would be some very large positive number. We'll call it V high. The equipotential surface there would be quite large. Over here would be a very large number, but it would be negative. So we'll call that V low. So this is a large negative number. Over here we have a large positive number. And now we're already at a point where we can start to imagine what intervening equipotential surfaces would have to look like. We're imagining that basically we're going to have to somehow morph from a sphere to a plane back to a sphere. So we can imagine that in between there's going to be some sort of distorted egg type shapes. Not really an egg, I guess, but you get the idea. Some sort of lobes like this. And these should look the same, but I'm not a good artist. So you should have sort of these symmetric lobes on each side, looking something like this. Now, in a future video, we're going to figure out that electric field lines always have to cross equipotential surfaces perpendicular. Actually, I've already seen that. So this will actually make it super easy for us to figure out what the shape of the electric field looks like. And also in future videos, we will be able to by doing clever differentiations to our voltage, get the expression for the electric field. It'll turn out to be a lot easier to do in the general case than directly integrating it out. Now, just for a quick note here, because this can look a little funny here, this is a case where making other graphs can be useful. So here, if I were to plot the voltage, I want to leave just that much up there. There we go. So let's go ahead and plot the voltage just as a function of our x-coordinate. And I'm imagining our x-coordinate is going right through the center, right through our charges here. So I'm going to plot the voltage. Well, right where our charges are located here and here, here the voltage would be going off towards infinity here. And here we would be going down towards infinity like that. And then in between, it's going from asymptotically from one infinity to asymptotically towards the other infinity, something like that. If you were to try to imagine this as like some sort of a 3D surface shape, you could be imagining a volcano sitting next to a whirlpool or something like that. So we'll close this one off by doing a slightly more complicated example. So let's imagine here that I have a charge of plus 1 microcoulomb here, and I've got a charge of 2 microcoulombs here. Q3 is 1 microcoulomb there, and then finally Q4 is plus 2 microcoulombs here. And again, let's say that they are sitting on a circle of radius 1 millimeter. And what I want to know is what is the voltage right at the center of the circle. So following our recipe here, we can just say that the voltage is going to be K times the sum over I, QI over RI, but here all of my R's are the same. So this is K sum over I, QI over just R, so that means I can pull that out of the summation. So it'll be K times 1 over R times the sum of my charges. All right, so let's go ahead and put in the numbers here. So this will be 9 times 10 to the 9 Newton meters squared per coulomb squared times 1 over 0.001 meters times the sum of, well, we've got 1 microcoulomb, which is 1 times 10 to the negative 6 coulombs, plus 2 times 10 to the minus 6 coulombs, plus 1 times 10 to the minus 6 coulombs, plus 2 times 10 to the minus 6 coulombs. So just doing this in our head, we can see that that is 6 times 10 to the minus 6 coulombs. All right. Now let's see, 6 times 9 is 54. So now we're just left with dealing with powers of 10. So this is 9 plus negative 6 is plus 3, divided by negative 3 is plus 6. This is 54 times 10 to the 6. And let's make sure that this is indeed volts. So coulombs will cancel 1 power there, meters cancel 1 power there, joule per coulomb. Yep, volt, good. 54 times 10 to the 6 volts, or if you prefer, 54 megavolts. This isn't a terribly realistic number, but it should at least give you some feel for how much easier it is to calculate the contribution to the voltage at a point from a whole bunch of sources than it is when you're having to do electric fields. Okay, so in the next video, we will spend a little more time looking more carefully at the electric potential for a dipole, and we will come up with a relation for the electric potential anywhere where you're reasonably far from the dipole. Catch you over there.